Suppose I asked you to roll a die, a fair die, six-sided die, 100 times. No, let's do 600 times. How many times would you expect the 5 to come up? Yeah, 100, right? 1/6 of the time, right? Now, if you actually did that experiment, would you expect exactly 100? Or if you got 102, would you be surprised? No, 102 is pretty close. What if you got 128? Would you be like, that's a little unusual? Or would you still be like, yeah, okay. You'd be fine with it? But the farther away you get from 100, I would guess that there's a growing sense of unease. It's like, well, wait a minute. That looks a little bit farther away from what I expected. So at some point, it does get a little bit too far, and we say, you know what? It's not matching our expectations. And there's another test that we can do that'll help us decide whether or not something actually does meet the expectations of what we think is going to happen. It's called the chi-squared goodness of fit test. Now, there's going to be two chi-squared tests that we're going to do back to back. This first one is a goodness of fit test. Basically, it's asking, does your expected values match what you actually observed? I mean, how close are they? I mean, you're not going to completely expect things to match, but you should be able to get pretty close. What's going to be different about this is the form of your null hypothesis. Your null hypothesis basically says that the frequency counts agree with what you expected. And the alternative hypothesis is that they don't. And we're not saying how they're different, we're just saying that they're different. This can be stated in other ways, and in practical terms, your null hypothesis can look like one of these. If you're talking about the gender of two kids, probability of both being boys is 1/4. One boy and one girl is 50%. Two girls, again, is 1/4. So that could be a null hypothesis. So you're talking about your frequencies or your expected values as percentages. Sometimes you'll have things that are all equal, like the probability that something happens is equal throughout the week. So you can just list that they're all equal to 1/7. So these are just a couple examples of a null hypothesis. In our dice rolling example, you could do that one as well. You could say h sub 0, the probability of rolling a 1 equals a probability of rolling a 2 equals a probability of rolling a 3, and so on. 4 equals probability of a 5 equals probability of a 6, and they're all 1/6. So that would be your null hypothesis. Your alternative hypothesis is that at least one of these is different. So at least one of these is different. You could also say that the frequency counts do not agree with the claimed distribution. That's a different way to approach it. See, counts do not agree with the claimed distribution. Both of them are ways of saying that what we observed is not what we expected. Now, let's actually do this test with some simulated data. We're going to get StatDisk to help us generate some data, and then we're going to test it. So let's go to StatDisk and go to Data. Down towards the bottom, hope that you'll see Dice Generator. Is that true on the Macs there, Chris? Got it? Okay, good. Let's go to Dice Generator. So for sample size, we'll make that a sample of 600. And we're going to roll one die. We're going to roll one die 600 times, 6 sides, random seed, put in whatever you want. Random seed is a way to help the calculator, or excuse me, not the calculator, but the computer generate random numbers to help you simulate rolling this die. So everyone should type in their own favorite number. I'll do 3, 1, 4, 1, 5, 1, 9, 2, 6. All right. Maybe you kind of get the joke here, digits of pi. But type in whatever you want, and you should get a bunch of numbers. Now, are they going to match mine? No, they shouldn't, and that's fine. The nice thing that we can do here is we're going to copy these with this little window right here, this little button, copy them, and then we're going to paste them back over into StatDisk so we can do some analysis. We can see, because I don't know about you, but I don't really feel like going through with a little pencil and paper and going, all right, I got a 6, I got a 3, I got another 6. I just want the totals here. So copy that, go back over to your data sample editor, and then paste it. So it should give you a lot of data here. And if you're not getting it, that's fine. Don't worry about it. You can just watch it up here. So let's see what our data says. So go back to data. This time we're going to go down to explore data and see some descriptive statistics. This is what column would you like to explore? Well, that'd be column 1. So let's hit evaluate, and let's see how we did in particular. Now mine, none of mine look terribly exciting. I got values of 107, 93, 102, 84, 109, and 105. And you should be able to see that from your frequency histogram. So 107, 93, 102, 84. 84 is kind of low on 105. But other than that one, none of these are terribly far away from what I expected. How about all of you? Did anyone get anything like more than 20 away from what you expected? No? Nobody? Okay. I mean, not surprising. Now, let me show you how you used to have to do this old school. So old school, we would do this this way: 107, 93, 102, 84, 109, and 105. So those would be our observed values. These are our expected values. And then we're going to do a comparison to try and figure out how the observed and the expected values look relative to each other. And the way that that works is with this. We're going to take and sum up the observed values minus the expected values and add it all up. But we've done stuff like this before, and we ended up with 0. So what we then did was we said, all right, well, we'll square this result. That way it's not going to add to 0. And finally, I'm going to add one more element. That is, I'm going to sum this up, the squared differences, and then divide it by the expected values. So O here is the observed count, and E is the expected count. And we're going to see how they compare. Now the nice thing about this is that this actually gives us a chi-square variable. And your chi-square variable is going to have n minus 1 degrees of freedom, n minus 1 degrees of freedom, where n is the number of categories. So in our particular case, since we roll a die with 6 sides, n is 6. So here, n equals 6. Our degrees of freedom then would be what?
5.
Good. Degrees of freedom would be 5. So in a chi-square distribution with 5 degrees of freedom is where you can find your critical value and your p-value. Now, fortunately for us, we're not going to have to actually calculate the p-value. We'll be able to get that from our work. Let's see how it would work in this particular case. What you could do, say with Google Sheets, is something like this. You could take, so you need to put the equals, parenthesis, there you go. The observed minus the expected, right parenthesis, and then squared, divided by the expected. Now the expected is in column B, so like that. Copy it all down, all the way down, and it's already been done for us. The last thing we need to do is sum it up. So in our particular case, where is the sum? Well, I'll just type it in, I guess. Equals sum of these 6 variables, or 6 values. This is what's called your test statistic. You would typically compare this to the chi-square distribution for 5 degrees of freedom. Let's take a quick look at that. So that table is in our book. F distribution. So for a chi-square distribution, chi-square distribution, 5 degrees of freedom. If we were doing this at the 5% level, 5% of the area in the right tail would put us right here, 11.071. So if your test statistic was greater than that, then you'd say, all right, I think we're going to reject. Now what has to happen in order for us to reject is that your observed minus the expected has to be pretty big. And the bigger this difference is, the bigger this total will be. And this will be far enough out in the right tail that we would reject the null hypothesis. So our test statistic, our critical value is 11.071 for a chi-square distribution with 5 degrees of freedom. And then you look at your actual test statistic. So your test statistic, let's see, where was it? Test statistic in this case for my data was 4.64. 4.64. Did any of these values seem really out of line with what you expected? Nothing really looks that far away. I mean, this one does look kind of far away, but it's not terribly far away. And you can see that these numbers aren't really all that big. They added up to 4.64. Let's take a look at how StatDisk would do this. Let's see, how do I want to do that? Let's close this out. I'm going to clear out this data and I'm going to type in my summary values. So in row 1, I'm going to type in the summary values: 107, 93, 102, 84, 109, and 105. Now, what did I expect? Let's put those in this column: 100, 100, 100. So those are our observed and expected. Make sure you keep track of which one's which. Let's go to analysis. Does it look like there's anything promising here? Yeah, goodness of fit. So let's go down to goodness of fit. And, you know, for giggles, let's just type in unequal expected frequencies. If you have equal expected frequencies, which really we do in this case, it'd be fine. But there's two ways to enter things if your frequencies aren't equal. You can enter them as proportions or you can enter them as counts. What do we have entered in our expected values? Proportions or counts? Counts. So from here, we can click evaluate and notice that it gives us the same test statistic, 4.64. It also gives you the appropriate critical value and the p-score. Let's take a look at that in terms of a plot. So your p-value is going to be the area to the right of this underneath the curve. It means it's basically telling you what's the chance that just by luck the null hypothesis is true and you're getting something that's as extreme or more extreme than what we saw. And the answer is, for us, it was like 40-some%, I think. What was our p-value? Yeah, 46%. So there's a lot of area here. Is this close to, or should we reject the null hypothesis based on this p-value? Darlene, what do you think? Should we reject or accept? Do you agree? Yeah, thank you. Yeah, we're going to fail to reject or accept. And I got to correct myself. I think the new thinking on this is to say fail to reject. But this doesn't even look close to rejecting, which is fine. It basically means that our random number generator that's helping us generate this data is doing its job. We're getting something that looks reasonably random, not too far away from what we expected. That's what a chi-square test is going to do for you. It's going to tell you how your observed values compared to the expected values. So let's go back here and write a conclusion for this. So we failed to reject. Should always put in the null hypothesis there. Make it clear that that's what we're failing to reject. Fail to reject H naught. There is not sufficient evidence to reject the claim that all six rolls are equally likely. Okay. So basically it looks like we have a fair die. At least the computer's acting like it has a fair die. Let's do one from the book, and then we'll do one that we generated our own data for. The one from the book is actually kind of an amusing one. I think the author is showing off a sense of humor again. I think it's problem number 8. A classic story involves 4 carpooling students who missed a test and gave an excuse as a flat tire. On the makeup exam, the instructor asked the students to identify the particular tire that went flat. If they really didn't have a flat tire, would they be able to identify the same tire? The author asked 41 other students to identify the tire that they would select. The results are listed in the following table, except for one student who selected the spare. Yeah, I couldn't get to the class. My spare tire went flat. All right. Uses 5% significance level to test the author's claim that the results fit a uniform distribution. Now, what does he mean by uniform distribution here? What would be, what's that? Uniform distribution. What would he mean by uniform distribution here? There's no variation? Okay. In what way? Does that mean they all select the same tire? Yeah, each tire had the same chance of being selected. So, H naught, you could say this in a couple different ways. You could say the probability of the left front equals the probability of the right front equals the probability of the left rear equals the probability of the right rear. So that's one way of saying it. Since there's 40 counts here, you could also say that those expected counts are each 10. If it were the case that this is a uniform distribution. But basically it means they're all the same, is what it's saying. So let's stick with what the author does in terms of the null and alternative hypothesis. The alternative hypothesis that the frequency counts do not agree with the claimed distribution. Frequency counts not agree with the claimed distribution. Okay. All right, so this, let's just keep track of it. That's our original claim. We're going to conduct this test at the 5% level. So alpha equals 0.05. And let's enter some data into StatDisk. By the way, how many degrees of freedom are going to be involved with our chi-square test? Yeah, we're going to have degrees of freedom equals 4 minus 1 or 3 degrees of freedom for our chi-square test. Okay, let's go to StatDisk. I can clear out a few of these things. Yes, I do want to clear that data. Now, the observed counts for the author were 11 in the right front, 11 in the left front, 15 in the right front, 8 for the left rear, and 6 for the right rear. Now, if, as the author claims, you know what, we already did frequency counts. If the author claims this is a uniform distribution, then each of these should have an expected frequency of 10. But what if I did it based on probabilities or proportions rather than frequencies? What would the expected probability of picking the right front tire or the left front tire be? 0.25. So let's do something a little different. Let's do 0.25 for all these. So we'll put in the probabilities as opposed to the proportions. Now, one thing that has to be true, this list has to add up to 1, just like our probability distributions earlier. I don't know exactly the tolerance that this thing has because, you know, sometimes there's going to be a little bit of rounding error. So just try and keep a couple digits and get reasonably close to 1 as far as the total of this is concerned. I can close this out. Let's go back to analysis, down to goodness of fit. Again, let's go to unequal expected frequencies. I know we do have expected frequencies. This time we're going to do things as proportions. So column 1 is where our observations were. Column 2 is the expected column. And it's going to work things through using proportions. So in order to do this, essentially what it's going to do, it's going to sum up this column. It'll figure out the total number of observations here, and then multiply those observations by these percentages to get the expected values. So n times p, just like your binomial random variable, calculating the mean there. Let's evaluate here. Test statistic was 4.6. Critical value was 7.8. Let's just take a look at that real quick. So in order to reject that claim, this blue line, which is your test statistic, would have to be bigger than 7.8, the critical value. So it's not, so you would fail to reject. But that's kind of doing it old school. We've been using the p-value here. So looking at the p-value, keeping in mind this is a 5% significance level, would you accept or reject? Yeah, accept. I keep on saying accept. I should say fail to reject, but yeah. So shame on me here. Fail to reject. So that's our decision here. Fail to reject H naught. Okay, so back to the hypothesis now. We want to word the testing of our claim. Go. Does your original claim contain the condition of equality? Yes. Do we reject H naught? No. So there's not sufficient evidence to warrant rejection of the claim that the probability of selecting a particular tire fits a uniform distribution. Okay. So again, please be careful in stating your conclusions, because the good thing for us is that we're able to kind of avoid / circumvent a lot of possible, a lot of the grunt work involved in doing a problem like this. So I am going to put more emphasis on making sure that you're stating the conclusion correctly and making your decisions correctly. We're okay with this one? All right. So before I started rolling tape on this lecture today, I asked you guys to come up with populations of some cities, real or imagined, fictitious, etc. And this is the data that you gave me, right here. So total all up. And let's take a look at this. We'll enter it into StatDisk. Now there's a couple things that we'll enter. We'll enter the observed frequencies, and I think I've got those here for us. So the observed frequencies were that the leading digit of all these imaginary cities was a 1 35 times. It was a 2 17 times, 3 16 times, 4 8 times, and then 17 for a 5, 5 6s, 10 7s, 10 8s, and 4 9s. Now, according to Benford's law, these kinds of data should have a distribution that looks like this. That is, the probability of leading digit being a 1 is going to be about 30% of the time. And then down to just under 18% for a 2, and 12%, 9%, etc. The formula, in case you're looking back at that and going, oh man, I don't remember Benford's law, it's this. It's the log of 1 plus 1 divided by your leading digit, which is going to be this one. And then you can copy that all the way down. So paste like that. Now what we need here is the probabilities. So you've got one of two choices. You can either do this in Google Sheets, or you can try and copy it down. But we're going to see if your data fits Benford's law. So I'm going to paste this into here. I hope it'll let me paste. Whew, good. For yourselves, you might just want to copy down a few digits. I don't think the StatDisk is going to let you type in the log formula that you need to calculate Benford's law. So let's just type in the first 3 digits. 0.301, 0.176, 0.125, 0.097, 0.079, 0.067, 0.058, 0.051, and 0.046. Now I'm hoping that it doesn't complain, because I'm not sure that this will total up to exactly 1 or not, but let's see. So let's test the claim that your data satisfies Benford's law. Think it's going to satisfy Benford's law? What do you think? You think you did a good job making up some of your own data, or is it going to be a mismatch with Benford's law? Any guesses? Probably off. I'm guessing that myself, but we'll find out. We'll do a test. We don't have to do it just based on guesswork. Do they? Oh, hey, cool. Cool. Does this column add up to 1? Yeah. Really? Oh, perfect. Excellent. All right. Well, let's take a look at kind of a little precursor here in this, and that is Benford's law. Data from Benford's law should look like this. That's what the distribution count should look like. If you did a relative frequency histogram, you'd see this slowly sloping curve. Let's see what our data actually looks like. I don't know. Could be, at least it starts out the right way. You have this huge spike at 1, and then it dips from there. But we'll find out how well our data matches. So we can write our null hypothesis in a couple different ways. Just for variety, and I know it's going to be kind of painfully long, I am going to write it out kind of long. Let's see, let me get back to the probabilities. So H naught p sub 1 equals 0.301. Comma p sub 2 equals 0.176. P sub 3 equals 0.125. P sub 4 equals 0.097. P sub 5 equals 0.079. P sub 6 is 0.067. P sub 7 is 0.058. And P sub 9 is 0.046. I did. So P sub 8, 0.054? 0.051. Thank you. Our alternative hypothesis here is that the frequency counts do not agree with the claimed distribution. Frequency counts do not agree with the claimed distribution. Okay, cool. Let's see how we did. So we'll go back to stat disk. Go down to analysis, goodness of fit. Certainly this time we have no choice. We have unequal expected frequencies. We've got them listed as proportions. There's one thing that I have to change here though. Does anyone know what it is? Expected column. My expected values for me are in column 3. They might be in 2 for you. It depends on what you did. But once you change your column, our significance level is set. We can click evaluate. Wow, this is so easy. You guys got it really good here. Well, how'd you guys do? Should we reject or accept that claim? Yeah, fail to reject. Oh, yeah, I'm like 0 for 3 today. Fail to reject. Yeah, fail to reject. So good on you. So coming back here, alpha was 0.05. Now, were you comfortably in the fail to reject region, or were you getting kind of close? Yeah, we're closer than before. All right, if you plot things, you're not too far away, but certainly, you know, a p-value of close to 11% isn't all that startling. So I don't know if this would raise suspicion or not, but you're certainly comfortably far away from rejecting in any case. So, failed to reject H naught. I'm kind of bummed because I wanted to state one another way, but good on you for coming up with good fraudulent data. There is not sufficient evidence that your fictitious data was made up. Oh. All right, let's state it a little different. There's not sufficient evidence to reject the claim that the data follow Benford's law. there's literally accounting software that takes advantage of Benford's law and checking for accuracy and fraudulent data. So, not that I'm hoping that you're going to be using that idea to circumvent that, but hopefully, hopefully not. What's that? Yeah, tax. I mean, there's software that looks for fraudulent data using Benford's law. So, are you comfortable with the goodness of fit test? Looking pretty good there? All right. For homework, try problems 1 through 19. Yeah. That's section 11.2.